Hello, everyone. So today I'm going to talk, thank you for inviting me to the new network theory reading group of the Lynx. So I'm going to present the work of Mairesse and Prabakhar on an element from queuing theory, which is the existence of fixed points for the GI1 queue. So I'll explain the terminology in just 1 second. So the motivation behind this talk is to sort of present on a mostly high level scale the mathematical tools and results associated with this object from queuing theory, which I will present, and sort of try to give at least a few examples of like applications and why this question is actually not just of theoretical importance. So since I don't know how well everyone is acquainted with the queuing theory, and since myself I'm not at all a specialist of queuing theory, I'll give the main ideas that you need to follow this talk. So when we talk about queuing theory, what we have in mind is a queuing model where we have some kind of node which has which provides some kind of service typically. There's an arrivals process that provides, let's say, customers or entities to the node. They enter a waiting area. Enter a waiting area over here, in which they wait until the service node can process them, and then they're transferred to an exit process. So this is the base object. And the questions of interest associated with this basic object are the questions of stability. So basically stability is concerned with does the service node actually process the arrivals, or is there an unstable behavior that results, for instance, in an infinite waiting area, so that there's sort of instability of the node. And the question of stationarity, which is if you let time go to infinity, does the behavior of the node converge to some kind of stationary behavior? So in some sense, is there some kind of asymptotic regularity of the node? Okay. So there's a notation that is going to be used, not much actually, but which is very standard in queuing theory, which is called Kendall's notation, which allows to sort of represent many different kind of nodes in a very synthetic way. So it can be kind of obscure when you see it for the first time, but once you understand the logic between it, it becomes kind of clear that what each node represents. So the idea is to represent this node, so this whole system, through a series of letters that are the characteristics of the node, of the queue. So the first letter is going to be to refer to the arrivals process. And so if you assume, as is usually done, that there's some probabilistic model involved, so the first letter will refer to the distribution of the arrivals process, and so the inter-arrivals process. The second letter will refer to the service time distribution, so the actual processing of the customers. So, and the third letter refers to the number of service channels, because here in this picture you have one node, but you could have many nodes in parallel servicing customers. So in the picture above, the C is equal to 1. And then there's 3 more parameters which are often omitted unless they're not the default parameters, because there's a default value for them, and so this, unless specified, it's always assumed to be the default value. There's the capacity of the queue, which is supposed to be by default is supposed to be infinite. There's the number of jobs that have to be served. So the idea is that whether the arrivals process stops after a certain time if this is not infinite, but by default it is. And finally, the queuing discipline. So by default, it's first in, first out. So if you have the first person to arrive to the node, will be the first person to be serviced. And the last person will be serviced last if there's a last person. So this is the queuing discipline. So the order in which the customers are served. So this is the basic Kendall's notation, and I will give a few examples. Yes,
Michel, excuse me. Can you explain again what N means? And the number of jobs.
Yes, N is the number of jobs to be served. So it's basically the number of people who will arrive to your node. So if your arrivals process basically stops after some time, so if you, for instance, you may have here, you have K customers to be served, then they will arrive one after another, and there will be the times between their arrivals will be given by this, but they will stop after a certain time if the number of jobs to be served is finite. And by default, it's infinite, so there's always new customers arriving to the node. Okay.
Okay, thanks.
Okay, so now I'll give a few examples. So I'd say the most basic queue is the MM1 queue. In the MM1 queue, the M starts for Markovian and refers to a Poisson point process. So it means that the inter-arrival times are distributed according to an exponential law. And so you have a Poisson point process that gives you basically the inter-arrival times of the node. And if the second M is the service times, so in the same sense, you have exponential service times for all the customers. And the one refers to the fact that there's one service channel. And so by the queues MM1, MMK, MM1, MMK, MM infinity. So those queues are referred to as the exponential queues. And so they can model many things there can be applications in, I don't know, I want to say actual customer service or of course in communication networks, or even in neuroscience, which is my motivation for studying this object. And so then another example which will be of great importance to us here is the MGI1Q. So the GI refers to a general independent distribution. So basically all the service times in the queue are i.i.d, and they have this, but we don't really say more about it. Whether it doesn't have to be exponential, it doesn't have to be, I don't know, Poisson or whatever. It's just fixed. It's i.i.d for all of the customers. And so in what follows, we're interested in a general independent queue, basically. So the point means that we don't assume anything on the inter-arrivals process. We assume that all the service times are i.i.d, and we assume that there is one service channel. And of course, so we assume there's an infinity missing here, but so there's an infinity of customers, there's an infinity of the queue has infinite capacity, and it's on a first come first served basis. It's still fine, first in first out. Okay, so this is the basic object that we're going to be interested in. So now this has been sort of an introduction about basics of queuing theory. Are there any questions about that?
Just one question.
Yes.
When you say that the dot can represent anything, so basically the inter-arrival times of successive customers can also be correlated with one another. So it would be like a GGI1Q, for instance.
Yes. And
okay.
it could be, yeah, that's exactly.
Okay.
And
thanks.
yeah, in what follows, we'll often assume that the inter-arrivals process and the service process are independent from one another, but we don't assume anything, I believe, on the inter-arrivals process itself.
Okay.
Okay, so now let me restate in a way that's going to be more clear, I hope, the goal of the results that I'm going to present. So we want to study the existence of fixed points for GI1Qs. So basically, we want to find inter-arrival processes with the same distribution as the inter-departure process they generate through the queue. So, so the idea is you have a queue, you have a process arriving to it, there's a process departing from it. We want to see, are there any fixed points, so processes with the same distribution when they arrive and then when they depart. The two, of course, are linked. And so one interest for that is to study the limiting behavior of the distribution of departure processes when you have an infinite tandem or an infinite tandem of queues. So a tandem of queues is basically you have a series of queues. And so when one customer arrives to a queue, he's processed by the queue. Let's say he arrives here, he's processed by the queue, and then he goes on to the next queue, and so on, and so on, and so forth. So you're always traveling from queue to queue. And so, of course, many different scenarios can be modeled in such a fashion. For instance, like the reason for which I was interested in this, so in this paper and in this kind of objects, is because I'm interested in cycles of neurons in neuroscience communicating with one another. And so I'm interested in finding their fixed points and the fixed points of such cycles. And so the idea is that, well, if you have an infinite cycle, we have a tandem of queues. So there's kind of a link between what I'm studying and between these kinds of models that I'm going to present now. And so I'll introduce a few notations, but I think I will introduce them again later. And so don't worry if you forget them right now. So we call S and K the service time of customer N in QK. So at the index N will always refer to customers, and the index K will always refer to queues. And A and K is correspondingly the inter-arrival times between customers N and N+1 in QK. Okay. And so we make a few assumptions. First of all, we assume that the A0, which is basically the sequence of arrival times for customers and at the Q0, we assume that A0 is ergodic, so it's an ergodic process. Is everyone clear on what ergodic is? I think so. I think yes. So it basically means that they have a convergence, sort of correspondences between spatial and temporal means in some sense, and that there's independence from the service times of customers at basically all queues. You assume that, so this is the GI hypothesis, that the S and Ks are i.i.d random variables. So S will always refer to the service processes and A's will always be rivals. You assume for stability, but I'll mention that later, that the mean service time is less than the mean inter-arrival time, basically, inter-arrival mean, and it's finite. So this hypothesis is needed in order for the queue to be stable. I'll come back to that later. And in order to not have a trivial case, you assume that the probability that the service times are not constant equal to their mean. So you assume that at least it's not a constant random variable in some sense. And so a known result by Loins is that for that all of the equilibrium departure processes, so all the processes AK, which are the inter-arrival processes from between for customers at node K, there are ergodic with the same mean. Okay, well, this is mostly sort of to paint a sort of a large picture. It's sort of used in technical arguments, but it's not going to be very important for us because I'm trying to stay mostly at a high level basis, so not delve too deeply into the math. So the questions that now we want to answer on this models are existence of fixed points. So namely, if you have an ergodic inter-arrivals process with mean alpha, does there exist such an inter-arrival process such that the inter-departure process has the same distribution? And if yes, we call it an ergodic fixed point of mean alpha. So and so another question which actually has been answered before the paper I'm presenting right now is the uniqueness of the ergodic fixed points under if it exists. So basically I'll mention this later, but basically we know that if there is an ergodic fixed point, then it is unique. And finally, the question of convergence. So assume now that there's a unique ergodic fixed point of mean alpha, it exists. The question is, if you have at Q0 you have the arrivals that are ergodic of mean alpha, do you have a convergence of AK, so the equilibrium departure or arrival processes at node K? Is there a convergence to this ergodic fixed point when K goes to infinity? So basically, is the fixed point distribution an attractor for the infinite tandem of Qs? Okay. So the idea is that as you go from Q to Q, if there's an ergodic fixed point, does the law of the kth Q converge as you go to infinity in the Qs to the fixed point? Okay. I hope this is clear. Please feel free to interrupt me at any time if anything is not clear, of course. And so, so these are the questions. And so what are the results as to those questions? So for exponential server queues, the picture is pretty complete at the time of the paper I was presenting already. So a reminder that exponential server queues are MM something queues. So when you have exponential arrivals and exponential service times. So first of all, there's a famous result by Burke, which says that the Poisson process with a given rate is a fixed point for exponential server queues with mean service less than this 1 over the rate. And so the paper I presented in the Diogene reading group a few weeks or months back, a paper by Anantaram, covered the question of uniqueness of this fixed point. Introducing sort of a Wasserstein distance to prove that the input-output map of the Q was contracting to show uniqueness. And there's a result by Mairesse and Prabakhar to show that this fixed point is unique and it's an attractor. So for exponential server queues, the picture is complete. And so for GI queues, so when you, instead of having exponential service times, you just assume i.i.d service time, but not necessarily exponential. The results that were known were that you had uniqueness of the fixed point, and that assuming the mean was finite, and assuming, of course, existence, then you had convergence. So you had the attractor. But so there were no proof of existence of fixed points. So basically, this paper. The aim of this paper that I'm presenting is to sort of fill in the hole in the picture for GIQs. And of course, I've mentioned before that why those objects are of interest. So the main result of the paper, which I'll slowly go, I'll ease you into it because actually most of the main results is in some sense irrelevant. I'll explain what I mean by that in a second. Actually, let me, okay, it's a bit better this way. So assume there's a few technical hypotheses. So first of all, you assume that you give you call beta the mean of the service time. If there's a technical condition, I need this too. Okay. If there's a technical condition, which is this one that is verified sort of integrability condition, then there's a set of values which is closed in B infinity. Which is kind of in some sense covers all of B infinity because its infimum is beta and its supremum is infinity. So there's a set of values such that if you are in the set, then there is an ergodic fixed point for the Q with mean alpha, and of course by the existing results it will be unique and attractive. So this is kind of the good case. So when you're in the set, you show that there is existence of an ergodic fixed point with mean alpha. When you're not in the set, things get a little hairy because basically you consider the fixed point. There is going to be sort of a fixed point, which is kind of a convex combination of ergodic fixed points of means alpha with I don't know how we call them, sort of underscore alpha and overscore alpha, where underscore alpha is the greatest value in the set that is less than alpha, and the overscore alpha is the smallest value that is in the set that's greater than alpha. And so the Cesaro average of the law of the first k interdeparture processes will converge weakly to this fixed point for the Q, blah, blah, blah. But it's kind of irrelevant because there's a very strong conjecture that I don't know if it has been proven yet, but at the time of the paper, it was just a very strong conjecture that was believed to be true, that actually the set S is the whole set of values between B and infinity. And so this whole thing doesn't really matter at all because this never happens. The idea is. So there's a kind of a description of what happens if the value of if the mean of the interarrival process is not in the set, but the idea is that it's kind of irrelevant. Okay, is the idea clear? Okay, I'm going to take the silence for a yes, and if not, please ask questions. So now
we nodded.
Sorry?
We didn't say anything, but we nodded.
Okay. Okay, sorry, I don't have the cameras. So now let me introduce the formalism for the GIQ. So actually, the idea here is to take this idea of a fixed point and formalize it in order to actually be able to state a mathematical result for fixed points formally. So the idea is here I will define, so the idea here is to define a Q as an input-output map. So the idea is that you take as an argument the interarrivals process and the service process, and you associate it with it a mapping that gives you the workloads, and another mapping that I'll introduce in just a second that gives you the interdeparture processes. So the idea here is just to see a Q. So this is not necessarily a GIQ, but just any Q as a mapping from the space of interarrivals processes and service processes into the space of you associate with interarrival and service processes. You associate basically mainly the interdeparture process. So the idea is, so what is you define the workload of customer N as the workload of customer N minus 1 plus the service time of customer N minus 1 minus the arrivals of customer N minus 1, and all of that only if this is non-negative, because otherwise, well, if basically if this is equals to 0, negative, the workload is 0, basically. And so you can rephrase that in this fashion. But the main mapping is the next one. The main mapping is the one that associates with the interarrivals process and the service time process, the interdeparture process. So there are many ways to describe it, which are all equivalent, but the most comprehensible one, the clearest one, is this one. Basically, it says that the departure time for customer N is given by the arrival time of the customer N plus the difference in workload between customers N plus 1 and customer N plus the difference in service times between customer N plus 1 and customer and the service time of customer N. Okay, so the idea, so you have the main idea is you have a clear way to define the main why are we doing this, because this is a clear way to define the interdeparture process as a function of the interarrival process and the service process. Okay, so this gives you the rigorous framework to study the interdeparture process as a function of the interarrivals process, which is exactly what we're interested in, because we want to see how we basically what we're doing, and this is actually my next slide, is to study the fixed point for this function, okay, for this mapping. And so a quick property that shows that these mappings conform to intuition. So when so if you take A and B to be sort of interarrival times, if you increase interarrival times, interdeparture times will also increase. And however, the workloads will decrease if you increase interarrival times, which makes sense, because if you increase interarrival times, then you basically have more time process your existing customers, so the workloads will decrease, and the inter-arrival departure times will increase because, well, you have to wait longer to see your next customer, basically. So this is kind of just a property that shows that it conforms to intuition. Okay, so now this is a very general model. So here we assume absolutely nothing. We just take abstract processes, and we just define mappings between define mappings. So, and we just use queuing theory terminology in order for it to make some sense. So we to justify the fact that this is the form of the mappings. Now we're going closer to actual queuing theory. We're defining the stationary queue. So basically, this is the stationary version of the previous queue. So you consider a stationary shift on your probability space. You consider processes A and S, which are assumed compatible with your shift, and that have a finite and positive mean. And so we call the basic, which are basically the arrivals process, the stationary arrivals process, the stationary service process. And now we define the stationary workload process and the stationary inter-departure process as the output of the two mappings that we defined previously for the arrivals, the stationary arrivals process and the stationary service process. And so we call this model a stationary queue. So a stationary queue is basically this mapping in some sense, because this one is mostly used to define this one. This is the most important one. And if the shift is ergodic, so here ergodic, it means that it's kind of well mixing, so that if the image of a set through the shift is equal to how should I put it? If you well, basically, if the inverse image of each set of value 1 is either a 1 or 0 is either respectively the whole set or the empty set. And basically, it means that just the shift is well mixing. And so if the shift is ergodic, then we call the model an ergodic queue. And so when which is exactly our situation. So if we take the GIQ, if the service times are i.i.d and non-constant, we say it's an i.i.d queue. And so the idea is for ergodic queues, there's a theorem by Loins, which gives conditions for the stability and instability of the queue. So the reminder, instability basically means that the workloads goes to infinity, and stability means that it stays finite. And so basically, this result says that when you have an ergodic queue, it's all conditioned by the mean values of the service times and the inter-arrival times. So for the first customer, for the first customer. So and so in what follows, we'll always stay on this event. So we're always consider the stable situation. Okay. Now, assume, let's call in what follows, we'll call sigma the law of the service process. And so we call phi sigma the mapping from the space of stationary measures on R plus Z into the space of stationary measures of R plus Z that associates with the measure mu, phi sigma of mu, where phi sigma of mu is basically the interdeparture process. It's the law of phi of AS. So this or A follows has the law mu, and S has the given law sigma, and A and S are independent. So basically, this is the queuing map because it associates with a measure of an inter-arrival, with the law of inter-arrivals process, the law of inter-departure processes. So a fixed point for the queue is exactly a distribution mu such that phi sigma of mu is equal to mu. And so what I've written underneath is the reformulation of the results of Lorenz from the previous slide. So if you have mean service time, so beta is the mean service time, which is which is here, this is beta. So if you have alpha, which is this, that is greater than beta, then phi sigma goes from the space of ergodic measures of mean alpha into ergodic measures, the space of ergodic measures of mean alpha. And if your Q is unstable, then your map goes from the space of ergodic measures of mean alpha to the singleton sigma. So this means that sigma is a fixed point, is always actually a fixed point for the Q, but it's called the trivial fixed point. So we're interested in the existence of non-trivial fixed points for the Q, because phi sigma of sigma is always going to be equal to sigma. Okay. So now we basically extend what we've defined to the case of the tandem of an infinite tandem of Qs. So now we just define exactly the same thing for stable i.i.d Qs, but now we assume there's an infinity of them, go with customers going from one to another. So basically you call S and Ks the i.i.d service times, and you assume their mean is equal to beta. And you call SK the service time basically of QK for all the customers, and we call sigma its distribution, and we consider A0 the arrivals at Q0. We assume that it's stationary, that it's independent from all the service times for all K, and that has mean alpha. We take theta the stationary shift so that all the processes considered are compatible with the stationary shift. And of course, there's an invariant sigma algebra associated, and we just assume stability. Okay, so this is just to say that we assume that our i.i.d Qs are stable. Okay, so and now we define, so for all the tandems, we all defined the workloads for all the Qs, and we define the interarrival processes at the Q. So AK is the interarrival process at the QK, SK is the service process, and WK is the workload process. And AK plus 1 is the interdeparture process at QK, and therefore the interarrival process at QK plus 1. So we're interested in the relationship between AK and AK plus 1. And so it's easy to see that AK, the sequence AK for OK, is a Markov chain. Because basically you can see that this only depends on AK, it doesn't depend on the previous ones. And so mu is a stationary distribution of AK if and only if mu is a fixed point for the Q. Because because if you have a fixed point of the Q, well, basically you can see that once you're in once you have the fixed point of the Q, you basically keep the distribution, the fixed point distribution forever, basically. So it's going to be a stationary distribution. And of course, reciprocate is always true. So the question is, we can reformulate the question now. So the question, are there any non-trivial fixed points for the Q, is equivalent to the question, does AK, the Markov chain AK, admit non-trivial stationary distribution? Okay. So now my goal is to present all the different results that have been in this new vocabulary, so as to sort of see exactly what is going on. And these results are actually used in the proofs for the existence. But I'm not going to go into the detail of the proof. I'll just present the main ideas of the different steps of the proof, because of lack of time, and I don't think it's necessarily relevant for here. And so for the uniqueness, the idea is to consider a Wasserstein-like distance. So what I mean by Wasserstein-like distance, I mean that you take two processes, which are going to be here, the arrivals process and the service process, and you look at the couplings of such processes. So basically you take you look at all by what do I mean by coupling is the set here is the set of all couples of processes such that the law of the first coordinate is going to be a given distribution mu, and the law of the second coordinate is going to be a given distribution nu. And so we consider the distance between those two distributions as the infimum over all couplings of a function of the two processes. And so the idea is that you're looking at the infimum, and so you can check that this is indeed a distance. It's not completely trivial. And the idea is that if you take a stationary Q, as defined previously, and you take two interarrival processes A and B that are independent from the service processes, and then the distance is, and then the function, the mapping between these input processes, and so this is the interdeparture process associated with it. So this mapping phi is going to be contracting for this distance. And so this is the main, this is basically this, from this you can easily deduce that you have a unique fixed point. Because once this application is contracting, well, you assume there are at A and B are two fixed points, and you'll get a contradiction. Actually, let me check. I think I made a mistake in the slide. No, it's correct. It is a large inequality here. But if you take an i.i.d, a stable i.i.d tandem model, because here this is just for in the general case, but if you assume i.i.d, basically then this becomes strict. Okay, so yes, sorry, this is an important point that I hadn't mentioned. So in the i.i.d case, in the i.i.d service case, there's basically a strict inequality here. Okay. Okay. Now, so never mind. I actually put it in the next slide. So if you consider a stable i.i.d model of infinite Qs here, with interarrival processes A0 and B0, with different laws, but which is basically the same mean on the invariant sigma algebra, and then basically there exists value k that after we value k, you have a strict inequality here. And so if you have one fixed point, basically you then in this case you have one fixed point, and you have attractiveness, and you have convergence to this fixed point under just the assumption of finite mean, and that you, of course, in the case of i.i.d service models, service times. And so a corollary for that is that if you consider the space of stationary measures of mean alpha that have a pathwise mean alpha, which is this condition, then there's an at most one fixed point in this space for alpha under the stability condition. And so in addition to that, so if there's a fixed point in this space, then it's necessarily ergodic. So it has to belong to the space of ergodic measures of ergodic distributions of mean alpha on the space of R plus Z, so interdeparture times. Okay, so this is basically the definitive result for the uniqueness and convergence of i.i.d for i.i.d Qs. Okay, so this is kind of the state of the art before this article. And so the main result of this that I'm going to present, and which I will give in a next slide, at least the main idea of the proof, is the following. If you consider a queue with an i.i.d. service process S, which satisfies that its mean is finite, it has it's non-constant service times, and you have a sort of integrability property, then there's exists an ergodic inter-arrival process independent from the service times, which satisfies a stable condition such that the corresponding inter-departure process has the same distribution as the inter-arrival process. So this is a definitive proof of the existence of the fixed point. So now I'll go into a little bit of detail into the idea of the proof. So the main idea, which is a classical idea in this field, is to consider Cesaro averages of the laws of AK. AK, I remind you, is the inter-arrival process at QK. And so the idea is you consider the quadruple AK, SK, WK, and AK plus 1. So you can see this. AK plus 1 in some sense is equal to DK, where DK is the departure inter-departure times for QK, and you call nu K the law of this quadruple. And so you take mu n as the empiric mean of nu K for all Ks between K and 1, 0 and n minus 1. And so you can see maybe nu n as the law of the quadruple AN, SN, WN, AN plus 1, where n is a uniformly distributed random variable over 0, n minus 1. So this is a uniform distribution, okay? And which is independent from all the other random variables of the problem, okay? So the first argument is to show that this sequence is tight. And to show that you use you use compactness arguments. There's something called the Tichenos Theorem, which is used here to prove that the sequence is tight. And then you use Prokhorov's theorem, which says that if you have a tight sequence, then mu n
Michel,
admits.
Michel, excuse me.
Yes.
I don't know what tight means.
Okay. Yeah. Basically, I think actually the easiest way to see it is through Prokhorov's theorem. It means that each subsequence of mu n has basically it means that mu n admits weakly convergent subsequences. Okay, so if you take a subsequence of mu n, you can basically, if you take mu n, you can construct a converging subsequence. Okay, in the weak sense, the convergence is weak, so it's a functional convergence. Okay, is that clear?
So it's a kind of Bolzano-Weierstrass flavor.
Yes. Tightness, basically, tightness is kind of the heart of weak convergence. So basically, a sequence is weakly converging if it's tight, and if the subsequential limits are the same for all the subsequences. Okay.
Okay, thank you.
And so so the idea is here exactly that. We want to show that you consider the subsequential limit of un, and so you consider sort of a quadruple distributed according to this subsequential limit. And so the main argument here is to show that this mu is kind of it basically is it's the same for all the subsequences. So by using you use the continuous mapping theorem and some properties of Cesaro averages to show that if you look at the distribution at the subsequential limit of mu n, the distribution of the inter-arrival times is the same as the distribution of the departure times. So if the idea here is that if you look at the Cesaro averages of the laws, if you take a subsequential limit, which you can do because the sequence is tight, so that this limit exists because of this condition, then you kind of have your ideal candidate for your fixed point, for the distribution of your fixed point. And the second, this is exactly the second part of the proof. You show that the distribution of the tilde is indeed precisely the distribution of phi of the mapping of A and S, which, as a reminder, have been defined here. So A hat and S hat are marginal distributions of this mu, which is the subsequential limit of mu n. And so this uses ergodic properties. And an important part is that for those 2 points, for 1 and 2, at no point whatsoever do we use the assumption that the service times SKs are i.i.d. This is true in a more general sense. So up to here, we have not used the fact that we are in a GIQ. Up to here, this has not been necessary. But now we have to verify that the fixed point that we have constructed here, so this A hat, we all have to verify that the law of A hat is not the trivial fixed point sigma. And this uses the i.i.d. assumption. This right here. This is precisely the point where you use the i.i.d. assumption. So I'm not going into the details here because it's yes.
Excuse me, Michel, again. Can you recall intuitively what would be the trivial fixed point?
The trivial so the sigma is the mean of the service times. So if you so this distribution is going to be a fixed point. So because if you take it's where is it the clearest?
So it's just the case where the continue.
Yeah, it's the trivial fixed point is the case where as your inter-arrival times are distributed have the same distribution as the service times, and they are i.i.d. So because, well, in this case, you sort of preserve the law because it's going to be another i.i.d. It's going to be another i.i.d. process with the same law, because you have the same law when you have a law that enters, you have the same law to process it, and then you have the same departure. So we're not interested in this trivial fixed point. So we are constructing here a fixed point which is not this fixed point. Okay.
Okay.
And this is needed because, yeah.
In this case, since the application is contracting, how is it possible that you have this trivial fixed point and also another fixed point?
Well, if you look at the conditions here, you're constructing a unique fixed point of a given mean.
Okay.
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 Okay. So okay, so it's basically I don't want to go into more detail into of the proof here because it's, I've tried to sort of take out all the non-technical elements so you could see the structure of the proof, but I don't want to go into the technical details. But if there are people interested, I could maybe go into it in another reading group session, maybe in the Diogen reading group, if people are interested. And so the last point that I want to discuss here, which I've sort of already mentioned in the beginning, when I stated the main result at the beginning, I want to study the values of the means for the inter-arrival process for which a fixed point exists. So what's the situation here? You consider a tandem of stable i.i.d. queues. You let phi sigma be the corresponding queuing operator, so that associates inter-departure process with an inter-arrival process given service process with mean sigma. And you could define the set S as the set of all the values of alpha, which are greater than beta for stability reasons, such that there exists an ergodic fixed point of mean alpha for the queuing map. Okay, operator. So it's clear now. So we're interested here in the values of alpha for which there a fixed point exists. So what we know from the previous theorem is that S, the set, is not empty. Okay, because what we've proven is that if you if this set was empty, basically there would only be the only fixed point would be sigma. But now we know there's another fixed point which is necessarily in this set. And so the conjecture is that this set is actually equal to the whole of beta plus infinity. So all the values of alpha greater than the mean service time, greater than the mean service time, will actually have a fixed point associated with them. But the actual result that is stated in the paper is that S is unbounded and is closed in beta L infinity. And so, in more precisely, if you consider an ergodic interarrival process of mean alpha in Q0, if this alpha is in the set, then everything works as intended. The distance is contracting, and you have convergence in this distance of the distribution AK to an interarrival process distributed as the unique ergodic fixed point of mean alpha, which is A alpha here. Okay. And so when you have weak convergence of AK to A alpha, because yes, I haven't mentioned it, but this distance is stronger than weak convergence. So if you have this, if this goes to 0, then you have weak convergence, but the reverse isn't true. But this is always kind of it's kind of like the Wasserstein distance, in this sense as well, because it's stronger than the weak convergence. And so if you're not in the set, this is kind of what I've quickly mentioned in the beginning, then what you have is that the empirical mean of the laws of the interarrival processes at Qi, so if you take the empirical mean for over K Qs, then this converges when K goes to infinity to sort of a convex combination of the law of the greatest value in S, which is less than alpha, and the law of the smallest value in S that is greater than alpha. And you even have an explicit value for the coefficient. So you have so basically you have a result on the Cesaro means of the laws of the interarrival processes. But the idea, so this is kind of both pretty and kind of horrifying. But the idea is that this doesn't really matter because there's a strong conjecture that alpha cannot be outside of S, because S covers all the values for which the Q is stable. So I actually don't know if this conjecture has been proven. If Francois, I don't know, I think Francois isn't here, but if he's here, he probably knows the answer to that question. But I haven't found the answer to that. I don't know if the conjecture has been solved, because this paper is from 2003, I think, which is quite recent, but still, so I don't know if it has been solved or not. But so yeah, so here it's kind of, the idea is you kind of have a nearly complete picture. So this kind of is only this is the only reason why I say nearly, because you don't know if S is all of beta infinity. But so you have a complete picture of GIQs, because you know that the stability conditions, you know that under the stability conditions, you know the existence and uniqueness and convergence for ergodic fixed points, which is kind of which kind of gives you all the information that you might need from the Q in some sense. You know, at least it carries a significant amount of information. I put it this way. Okay. Okay, so I think my time comes to an end, which is great because my slides come to an end as well. Thank you for listening. I hope it was clear and not too abstract and notation heavy. I've tried to always kind of focus on the concept rather than the necessarily the technicalities behind them. So thank you for listening, and if you have any questions, feel free to ask.
Thank you, Michel.
Are there any questions? So maybe I have a small one. So if I understand well, the moral of the story is that as soon as you have an arrival rate that is not too big, too large, things go well, and essentially you converge to
yes,
to a fixed point when k tends to infinity.
Yes, exactly. So basically, yes. So why is the study of, which I've mentioned, that the study of fixed points is interesting because it gives you the stationary distribution for the infinite tandem of cubes. So if you have many, basically, if you have many cubes, then you will converge, assuming that yes, that you're stable, then you will converge eventually to the stable to this fixed point distribution for the. And as far as I know, we don't know the speed of convergence, but we know that I don't know. Yeah, maybe you have some results on the speed of convergence from Markov theory, but I don't know. But yes, so this is the description of basically the behavior, the asymptotic behavior for the infinite tandem of cubes.
So just a small question, because most of your results concern the mean of the distribution. So you have mostly conditions on the average.
Yes.
The average departure time. So you don't have any condition. For example, if you take some kind of weird distribution with a heavy tail, for example, it doesn't affect the result that you have for your convergence.
Well, you have a sort of condition on the heavy tails for the service.
Yeah. Okay. So kind of for integrability. Okay.
Okay. Yeah. But there's no condition for the arrivals process. Well, you just have to, on the inter-arrivals process, the only condition is on the mean.
Okay, that's interesting, actually.
Yeah.
And so finally, when k tends to infinity, the limiting distribution does not depend on the input distribution, but only on the expectation of the input distribution.
Yes, exactly. Yes, because the fixed point is given the mean. Yeah.
Yeah. So, do you see some implications of that for your domain of interest, which is neuroscience?
Well, it's kind of fresh because the idea is that my cycles are not exactly they don't really fall exactly into this into this category, because there's my cues are kind of they have very specific very specific functioning. They basically they are they basically, the idea is that when you're kind of their input the input increases the sort of the value stored in the queue, and then periodically you reset the value in the queue. You sort of and you send the customer to the next queue. But because of this reset, it may there's some weird weird stuff going on. So the idea is just here to study sort of results for simpler models and try to see how they relate. But for now, it's not very clear to me. So this is, it's kind of very new to me. So I'm just in the process of learning now.
And do you know of other applications where this notion of a tandem of queues and of limiting distribution when k tends to infinity might be of interest, practical
yes,
applications?
I think they were widely used for in communication networks. So you can if you because basically these queues arise. These infinite tandems of queues arise as let me check. So basically, yes, they basically okay, this is not. Let me check. I have another notes where I think I mentioned why this is important somewhere. Yeah. So So the idea is that you can sort of, if you have you can compute stationary performance quantities for the queues. So the idea is that sometimes when you look at these infinite tandems of queues, you can see them as networks of kind of very specific networks of queues, which arise in certain network models. But it's actually, yes, it's not my it's not exactly my field, so I don't know more than that it's used. I know that it's used, but I know it's not. I don't actually know exactly what for, because
Okay,
yeah, my relation to it is more like a tool and rather an object of study.
I just have a comment on that point. What I understood on all this aspect, I do not understand all the details, but I think I understood the philosophy behind. For large networks, when you have some paths with large paths, morally, what I understood with this kind of result is that the behavior of the traffic at the end of the path will be something close to the limit you calculate, in fact, with this theorem. Do you have this theorem? Am I right? Or
yeah, that sounds about right. Yes.
And so I have a question on my side. So here, there is a proof of existence.
Yes.
But do we have some information about the shape of the distribution for this limiting point? Limiting the distribution.
Well, we know it's mean, but apart from that, well, I don't think so, actually. Yes, it's a very good question.
For me, this would be the interesting part, in fact.
Yeah. Well, yeah. We kind of constructed it kind of explicitly here.
Yeah.
So yes, in some sense
we have something that we can construct it with the Cesaro mean, I think, also.
Yes, exactly.
But
so yes,
because it doesn't depend. How to say? In fact, it appears it's a bit like if there was only the means that count. Make me think that maybe we have something. I don't know if you have something about the other moments of this limiting distribution.
Well, as you can see, everything depends on this empirical mean. So this is what kind of gives you the construction of this. So so if you since you assume you know everything is sort of in UK, you can sort of construct explicitly this a hat through it, I think. But
Yeah,
It's a bit like, for example, it's a bit like if, in fact, the arrival distribution doesn't count. Initial arrival distribution doesn't count, in fact. So
yeah, only the mean counts. But
so maybe
sorry,
there is a strong relation with the service, with the service distribution in that case, and it may depend only on the service distribution. I don't know. It's just
well, yeah, they're both kind of contained in here. Okay. But because these are functions of these, but yeah, but it's kind of how should I put it? An average. There's kind of an averaging effect.
But in particular, if you want to compute the distribution, you can consider compute the limit distribution. You can consider the case where the arrival times are constant, because it will give you the same limit distribution as any input distribution that has the same average.
Yes, I think that will be true. But yeah, there's yeah, you have to assume that the service times are not constant. But yeah,
yeah. But once the distribution for the service time is given, and say you want to know what is the limiting distribution for an arrival process with a mean alpha, if it simplifies the computation, you can consider an arrival process with which is with a constant time.
Yeah. Yes. I think yes, indeed.
So I was thinking more in terms of application and relating to Ludovic's question.
Yeah.
Because if you have explicitly the distribution for the service time, maybe by considering the case where the arrival come in constant time, it will simplify the computation to determine the limit distribution.
Yes. Yeah.
And I have a last question about so the condition of convergence with a probability to the power 1/2.
Yes.
In this slide, this is a question I have. It may I think it is related somehow with Evitail distribution, but I don't see exactly how here. And then, do you know the relation with Evitail for this condition?
So
I fear that if you have something that is a bit Evitail, the condition is not. But I'm not sure that
so,
the condition is not verified.
Are you asking for sort of an explanation for this condition, or rather than the relation between this condition and the tails of the?
Yeah, more the last point.
Well,
it is a factor 1/2 that makes me think that we may have something that is not compatible with Evitail that we can find in, for example, in telecommunication network.
Maybe honestly, I don't know. I'm not.
I will have to think about it by myself after, but I don't see the exact relation, in fact. But I'm interested in it.